Alright, welcome back everyone, and we're just going to finish off this tutorial by putting in our signal timings. So I have on the left side of my screen here, I have a signal timing sheet for the intersection of Columbia and Phillip Street. And it tells us quite succinctly, actually, the timings for the intersection. And so you'll see in industry, you'll see a lot of different styles of signal timing sheets, but in general, you're looking to pick out these kinds of values. So min and max green time, amber, all red. These are the values that we really need in order to conduct an operational analysis. And sometimes you'll get large packages which have the entire signal coding for the intersection, but really this is what we're typically wanting to pull out and input. So back in VISTRO now on the right side here, we'll go through and input these values. So the first thing we need to do is we need to define our priority scheme. And this just defines which road is major and which one is considered minor. And that has an impact on how we define our signal phases here later on. So typically, of course, the major road is the one that has the larger traffic volumes, and in this case, because of that, Phillip Street is really considered our minor road. So we're going to make that adjustment here. Just click on the drop down and change Phillip Street to minor if it's not already like that on your computer. Next thing here, obviously we want to analyze this intersection eventually, so we'll leave that. We leave the 15-minute analysis period. The other thing that we want to adjust here potentially is whether or not the intersection is located in our central business district, or CBD. The reason we want to check or uncheck this box is that the downtown context with its closely spaced intersections and dense urban area tends to have an impact which lowers the saturation flow at a signalized intersection, and that of course has an operational impact on the intersection. In this case, Columbia and Phillip is not really near Waterloo's downtown, so we're going to have this box be unchecked. So if it's already checked on your computer, please uncheck it. And then the next input we have to make here is the cycle length. So if we look over at our timing sheet, we're going to be picking the signal timings for the AM peak hour in this case. So that's 7 a.m. to, well, the peak time for this phase is 7 a.m. to 10 a.m. The peak hour would be some hour within that. And it doesn't, there's nothing here that explicitly says cycle length, but at the bottom here they have a total, which is all of these values added up, and so our total is 100 seconds, and we're going to take that as our cycle length. We will leave time of day pattern coordinated and fixed time, because at the top here we're given a bit of a description about the intersection, and it says that we're operating in fixed time and that our signals here are coordinated with surrounding signals on Columbia Street. Next thing we have to input is our offset. So when you have a coordinated corridor of signals, obviously to keep that coordination for cars along the main road, you need to offset the time between when green lights occur at one intersection and the next intersection. So typically we measure that in seconds, and that's what VISTRO is asking for. But here on our signal timing plan, they give the offsets as a percentage of the cycle length. So here you can see our offset for the AM peak hour is 28%, and in a 100-second cycle, that's just 28 seconds. And then these last 4 lines here, we're just going to leave those as is. The next part here is the phasing and timing section. So I'm just going to minimize the intersection settings, and we're going to work here. So the first thing we need to adjust is our control type. And control type basically refers to the type of phasing for each movement. And what do I mean by that? So for example, for our left turns at this intersection, you can see here they have the ability to display an advanced green arrow. And this type of phasing is called a protective permissive phasing. And what that basically means is that the left turn phase has 2 parts to it. There's a protected portion where you get the advanced green and you can make your left turn unobstructed by any other movements. And then there's a permissive phase where the opposing through movement usually turns green, and you can enter the intersection and wait to make a left turn, but you're waiting for a sort of permission, in other words, an acceptable gap in the traffic to actually make your left turn. So all of these left turns have the ability to display a protected permissive phasing. And you can see here on our signal timing sheet, we have some information about how long each protected portion of the green arrow will get. And it is worth noting, here you'll see we have values for eastbound green, westbound green, and northbound green. So these are all our left turns. However, we don't have one for southbound. And what I'm going to infer from that is that during the AM peak hour, the southbound left turn movement does not actually get an advanced green arrow. So this is something you might see from time to time in signal plans. Not all phases are always turned on throughout the day. So it's important to pay attention to that. So what we can do is we can go in here and we can change our control type as needed. For northbound left, we're going to have it set to protected permissive. For the southbound left, because there's no protected portion during the AM peak hour, we're just going to set it to just permissive. In other words, if you want to make a left turn during this AM peak hour in the southbound direction, you have to wait for a gap. And then for eastbound and westbound, those will also be protected permissive. And then the next part we can do here is we can define basically the labeling of our signal groups or signal phases. And the way we do this, there's actually a convention that is used. It's called NEMA phasing, N-E-M-A. And you can find it basically by searching NEMA phasing or FHWA, which is the Federal Highway Administration. They have resources on their website basically defining what these conventions are. And the short version is that the convention is that the major movements, the major through movement phases are labeled 2 and 6, and then the minor through movements are 4 and 8. The major street left turn phases, if there is a protected phase, they get their own separate phase number. And so for the major street, that's 1 and 5. And then for minor street, if there's a protected phase there as well, those will be labeled 3 and 7. So we're just going to basically copy this diagram and enter all of that in. So for our northbound left turn, you can see here that will be phase 3. For our northbound through, that will be phase 8. Southbound, we don't have a left turn again, so we're just going to take the through phase, which is phase 4. Columbia Street, eastbound left is phase 5. Eastbound through is phase 2. or westbound left is phase 1, and westbound through is phase 6. All right. And now we can move on. We can start to fill in this, but I'm just going to show you, I'm going to skip a little bit ahead here to the sequence tab at the bottom. And the reason I'm going to do this is just kind of to show you where we're going, and also then when we put these values in, there will be a diagram at the bottom here that will update live, and you can see how inputting different values actually affects the timing plan. So in our sequence here, basically this is our ring barrier diagram which we have to define. So some softwares will do all of this stuff automatically, but in VISTRO we have to define it ourselves. So because of the way we've set up this phasing here, we can do a really easy thing, which is in our ring 1 row, we just go 1, 2, 3, 4. And in our ring 2 row, we can just go 5, 6, and then because we don't have a phase 7, we're going to go to 8. And the only other thing we need to do is we need to add in a barrier, so this line here, and we can do that just by single clicking on the line where it should be. And so now you can see it's displaying a diagram here. This doesn't look like a complete timing plan yet, obviously, but as we go through here and put in the values, it will start to fill itself out a bit more. So I'm going to pull up the timing plan again, and we're going to go through each of these movements. So starting here with the northbound protected permissive left turn. So our minimum green is 5. Our maximum green is going to be 6. Our amber arrow is going to be 3 seconds. So that's 3 seconds of a yellow arrow. And the all red for that arrow is going to be 1 second, which matches the defaults here. As well, vehicle extension. So because there's detectors in the road, sometimes phases will be extended. So we can set our vehicle extension to 3 seconds to match the timing plan. All right, and then we will move on here to the northbound through. So in this case, again, so depending on where the timing plan comes from, there are varying levels of detail that will be included in it. So in this case, you can see that for our main movements here, we don't actually get a minimum green time. So I'm just going to leave it as the default and input this value here as the max green time. And so what we can do then is we can just repeat that for every other intersection movement. So for the southbound, we're going to assume that that's the same as northbound, and then for the eastbound and westbound. So for eastbound green arrow, the minimum green is 5 seconds. The max is 10. With a 3 second amber and a 1 second all red. Once we put our minimum and maximum green times in, we would just put the amber and all red for the through movement. So amber for the through movement is 4 seconds, and the all red is 2 seconds. And then we're just going to do exactly the same thing on the southbound through movement, because we're just going to assume that it's the same as the northbound through movement. And then we can do eastbound um, eastbound left turn. So 5-second minimum green, 10-second 10-second max green, 3-second amber, 1-second all red, and then for the through movement, that will be a leave the minimum green, 38-second maximum green, 4-second amber, 2-second all red, and I'll just do the same thing here quick for the westbound through movement. And then the last thing I have here is the westbound green arrow, which you can see actually has a slightly different timing than the eastbound green. So still minimum 5 seconds, but the maximum green is only 6 seconds. Alright, and the next part we can do here is we can input our splits. Now, splits are really probably the most important number here for visualizing your signal timing plan. And the split is basically the sum of the green time, the amber time, and the red time. So it's the total time that each movement gets within the signal cycle. So what we're going to do is we're just going to add those numbers up. So we'll take our max green and add to that the amber and all red. So for our northbound left, that'll give us 10 seconds. For the northbound through, that will give us 26 plus 4 plus 2, 32. Same thing for the southbound movement. And then for our eastbound left, that will give us 14-second split. For the eastbound through, that will be 44 seconds. For westbound left, has a slightly lower max screen time, so that'll just be a 10-second split. And for the westbound through, it'll be 44 seconds, just like the eastbound through. And now you can see at the bottom here that our visualization of our signal timing plan is really starting to take shape. You will notice, because of how we've calculated our splits, not every single one of these phases actually fills up each half here of our ring barrier diagram. That's fine. It's not a big deal at all. But what we could do is if we did want it to show that, then we could make some adjustments to our splits here. So we could, for example, extend signal phase 2 for another 4 seconds here to fill it out. But the important part really is that the total length of our cycle, if we add up all of the longest parts here, that the sum of all these splits adds to our cycle length. And so we'll just check that. 14 plus 48, 58, plus 10, 68, plus 32, 100. So we're good. And you might be wondering as well, what are these weird other groups at the bottom here? These are our pedestrian phases. So signal group 102 is the pedestrian phase that's associated with signal phase 2. And we can go in and we can add those as well from our signal timing plan, especially because we're given them. It's not always necessary to do that, but we can do it just for the sake of the example. So I will add in 13 seconds on the northbound and southbound walk. And then, 13 seconds walk, and then 13 seconds flashing don't walk, which is another word for pedestrian clearance interval. And then for the eastbound movement, 25-second walk and 13-second flash and don't walk. Same thing with our westbound movement. And you might be wondering, how do we determine these? We'll, depending on which course you're taking, you'll likely talk about how we determine each phase of the like the vehicle signals. But for the pedestrian phase, all you need to know is that these times are just a function of how long it takes to cross the street. And yeah, so once we've done that, there aren't many other settings that we need to deal with here. We can, if we had other intersections, we could check coordinated for the major street through movements. We can also check, in this case, because we're doing a fixed time operation, we could check off max recall. But for the most part, there's not a lot else here that we need to change. We could also add in actual detectors, especially for our actuated left turns. But all of these, especially the detector, doesn't typically have a huge impact on the final operations. But now that we've done all of that, that's basically all we need to do for the signal timing. So you'll see that our menu here continues for quite some time, but all of these values are in italics, which means that VISTRO is calculating them for us. So there aren't actually a lot of inputs here that we need to deal with. But what these are basically are the results of our analysis. So if you scroll down here, you'll start to see our results. So like volume to capacity ratio for each lane, or for each movement rather. You can also, or sorry, this one is for each lane. There is another area here for each movement. And then you get delay for each movement in each lane. Hey, Future Chris here. I realized after recording this that I forgot to do something that I said I was going to do, which is edit the base saturation flow rates. So the way you can do that is you go down here under the saturation flow category, and you can see here everything in this section is currently italicized, including the base saturation flow. But we can edit it by checking the checkbox right underneath, and then we can define our own saturation flow. So I'm going to do that for all of the lanes. And then I'm going to define a different saturation flow per the region's requirements. So for a, pin that to the left side. So for a single dedicated left turn lane, we're going to have a saturation flow of 1775. For a shared through right lane, saturation flow is 1650. Same thing for the southbound approach. And then for the eastbound through movement, we're going to use the two lane through right here. Or sorry, the data inputs are slightly different from synchro. So in synchro, you would use the 2 lane through right, but because we have the option to break it down by each lane here, I'm going to use the through lane value and then the through right lane value. So that's 1900 and 1650 again. And I'm just going to do the same thing for the westbound approach. $1900 and 1650. So there's not anything more we need to do, but I will just show you as well A couple other things we can do here. So once we have our results, we don't want to just take a screenshot, obviously, so we can export as a report. So we can go here and print a report. It'll basically give us this table, and we can select what details we want to include. Other things we can do as well. So let's say we wanted to make some changes to this intersection. Maybe we wanted to better optimize the signal time, because you can see we have some movements that, while they are performing somewhat acceptably, it's possible we could improve them. So one of the things that VISTRO is very good at is developing new signal timing plans or optimizing an existing plan. So if you come to the top right here, there's a couple options related to that. One option here is there's a checkbox. So what this will do is if you check it, it will automatically re-optimize the signal timing plan at every time you update something in the network. We're not going to do that today, and typically we want to have a little bit more control over how we're adjusting our timing plan as engineers. But it gives us a couple other options. One is we can create a default signalization from scratch and let the program do that for us. Or, and this is more commonly what we would do in a traffic study, is we would want to have some control over optimizing the splits or re-optimizing our cycle length. So typically, just for your reference, if you're doing a traffic study, unless you have been explicitly told that you can, typically you do not want to be adjusting the cycle length. And the reason for that is, depending on the municipality that you're in and the surrounding context, changing the cycle length will have impacts on any signal coordination in the corridor. So you remember that in our case here, this is a coordinated corridor. And so what that means is, to have coordinated signals, all of the cycle lengths along the corridor need to be equal. And if you change one of the cycle lengths, then that will have impacts on the coordination between each signal. So typically we don't want to be re-optimizing the cycle time. More often we would do something like this, where we click up here and we can optimize our splits. And there's two objective functions that VISTRO uses to perform this, and which one you pick depends really on what critical values you are using. So what is a critical value? Well, typically, if you're doing a traffic study, the municipality that you're doing it in will have some form of criteria for what denotes a problem movement or a problem approach or a problem intersection. And then and those are based on performance measures. So things like level of service, volume to capacity ratio, or queue length. And so very commonly you'll see something along the lines of, if the movement is performing at level of service E or worse, so in other words E or F, then further remedial measures are required. So what this function does is it allows us to prioritize. So sometimes you might also see, instead of it being based on delay or level of service, it's based on volume to capacity ratio. So a volume to capacity ratio of 0.9 or greater, for example, is considered critical. So depending on which ones you want to minimize, you can pick between these objective functions. Right. And with that, that concludes this tutorial. Hopefully you enjoyed, hopefully it was useful.